Hey, welcome to The Explainer. Today, we're diving into the hidden science that keeps our giant skyscrapers standing tall even in the middle of a massive storm. It's this constant, invisible battle between incredible engineering and one of nature's most powerful forces, the wind.
Okay, let's just jump right in with a question I bet you've asked yourself, right? You look at a city skyline, the wind is howling. How do these massive towers, hundreds of feet in the air, not just tip over?
Well, the answer starts with understanding that wind is way more than just a simple push. To an engineer, wind is like a complex, invisible attacker. It has a whole bag of tricks it uses to try and bring a building down.
Now, we all get that straightforward push from the wind, but it's the forces you don't feel that are often the most dangerous. Take something called vortex shedding. As wind whips around a building, it creates these little swirling whirlpools of air on either side. This creates an unpredictable side-to-side push that can get the building vibrating, swaying, and in the worst cases, literally gallop itself apart. It's pretty wild.
So to fight back against this invisible attack, engineers don't guess. They use a very precise and detailed rulebook. For this explainer, we're going to look at the Bangladesh National Building Code from 2020. It's a great example of the scientific framework that engineers all over the world use to tame the wind.
At the very heart of this code is a formula that you can think of kind of like a recipe. It's a method that lets engineers take the wild, chaotic force of the wind and turn it into a single, predictable number, the exact pressure that wind will put on any part of a building.
And here it is, the core recipe. I know, it looks like a bunch of alphabet soup, but don't let it intimidate you. Just think of it this way. Each of these variables, the Ks, the Kaz, the V, the I, they're all just key ingredients. Each one helps us answer a very specific question about the building and its environment to get our final result.
So let's do it. Let's break down that recipe and look at each of those 5 key ingredients one by one. Because really, understanding these is the secret to how engineers tame the wind. All right, first things first, the recipe needs its most basic ingredient, right? And that is the raw, pure speed of the wind itself. But it's not just any wind speed. And this part is absolutely crucial. Engineers don't design for the average wind speed you hear on the weather report. No way. They design for the absolute worst-case scenario. We're talking about the most intense 3-second punch that a storm is statistically likely to throw at that specific location. That becomes the baseline power of the storm they have to defeat. Okay, next up, the recipe asks a very important question. What's at stake here? What happens if this building fails? Because let's be honest, not all buildings are created equal. This is where something called the importance factor comes in, and it's basically a safety multiplier. For buildings that are absolutely critical to public safety, a hospital, a fire station, this factor actually increases the required wind resistance. It forces engineers to build them even stronger. It's like a built-in shield for the buildings we need the most in an emergency. This table lays it out perfectly. So a standard office building, that has a factor of 1. But a hospital or a school, that gets bumped up to 1.15. That means it has to be designed to withstand a 15% greater wind force. Then on the other hand, you have something like an agricultural barn, which poses less risk. It actually gets a lower factor of 0.87. The third ingredient is all about the neighborhood. You see, a building's surroundings can dramatically change how the wind behaves long before it ever even gets to the structure. This is called the exposure category, and it's all about the roughness of the terrain around it. I mean, think about it. A dense city full of buildings acts like a thick forest. It creates all this friction that slows the wind down near the ground. An open field, on the other hand, offers almost zero resistance. And this comparison just makes it crystal clear. A building out in an open field, what engineers call exposure C, is going to experience much higher wind forces near the ground than the exact same building nestled in a dense city or exposure A. The code actually adjusts the pressure for each different scenario. All right, our next ingredient zooms in even closer. It looks at the specific piece of land the building sits on, because the local landscape can act like a natural ramp, accelerating the wind to even more dangerous speeds. This is the topography factor. If a building sits on the crest of a hill, the wind is forced to squeeze up and over it. This compression makes the air speed up. It's just like putting your thumb over the end of a garden hose. This factor makes sure the design accounts for that speed up, increasing the pressure. And finally, our recipe includes a little dash of statistics. Engineers consider probability. I mean, what are the actual chances that the strongest possible wind will come from the exact direction that puts the most stress on the building structure? This is called the wind directionality factor. It basically acknowledges that it's statistically pretty unlikely for the absolute strongest wind to hit the building from its absolute weakest angle at the exact same time. So the code allows for a small reduction in the total calculated force. It's a really smart adjustment that keeps the design incredibly safe, but also economically efficient.
So, what happens when we mix all 5 of these powerful ingredients into our formula? Let's take a look at what we actually get out of it.
The output isn't just one number. By applying this whole recipe, engineers create a detailed pressure map. This lets them calculate the precise force the wind will exert not just on the building as a whole, but on each individual floor, each wall, and even each window, from the ground all the way to the very top.
And this chart shows one of the most critical takeaways from that map. Wind force is not uniform, not even close. Because the wind gets faster and stronger the higher up you go, the forces on the top floors of a skyscraper are significantly, massively greater than the forces down near the ground. So what's the biggest takeaway from all of this? Well, it's that the safety of our modern cities relies on this meticulous, hidden science. It's a process that takes the chaotic, unpredictable force of wind and turns it into a set of numbers that engineers can use to design an invisible shield around every single one of our structures. So the next time you see a skyscraper swing gently in a storm, you won't see a building in peril. You'll see a masterpiece of engineering performing exactly as it was designed to. And it kind of makes you wonder, right? Now that you know the recipe for wind, what other invisible forces do you think are out there shaping the design of our world? Thanks for joining me.